Hey everybody, welcome to podcast number 12, where we're going to look at what if we have a buffer and we add a strong acid or strong base to that buffer. How is that going to change our overall pH? Well, recall that when we add a strong acid, right, to the buffer, right, it is going to react with the weak base, and we're going to produce a weak acid, right? And otherwise, if we have a strong base and we add it to our buffer, it's going to react with the weak acid and convert it into weak base. And so when we do this, right, we're converting one weak species to its conjugate, whether that be the weak base into its conjugate weak acid, or whether we're converting the weak acid into its conjugate weak base. And so what happens then is that we are changing, right, the acid to base ratio. And remember then that that was our H plus is equal to Ka times the weak acid number of moles divided by the weak base number of moles. So this changes. And so that means that the H plus concentration also changes. So we're going to change our pH overall. Let's take a look here at sample problem 18-13, where we have an aqueous solution and it is 0.043 molar weak acid. And this is some generic weak acid that we're going to call HX. We're given its pH, and I want to know, what is the pH if 0.021 moles of KX, all right, so this is going to be the weak base. So the conjugate weak base of that is dissolved in with 1 liter of the weak acid. So what we're doing then is we are taking our weak acid and we are going to make a buffer by adding some of its conjugate base. So first off, it says that we want to calculate the H plus concentration and the Ka. Well, our H plus concentration is going to be equal to 10 to the minus pH, which is 10 to the minus 3.92. So we get 1.2 times 10 to the minus fourth. All right, and then, right, this is still just going back to problems that we've solved before. So our Ka is our H plus concentration times our X minus concentration. They're going to be the same, so I'm going to say H plus squared divided by our HB, which in this case is our HX concentration. So we've got our 1.2 times 10 to the minus fourth squared divided by, all right, in the problem we have 0.043, and I'm going to subtract off 1.2 times 10 to the minus fourth, just to make sure that it's at equilibria, right? Because that's the initial. If I subtract off the 1.2 times 10 to the minus fourth, then this becomes at equilibria. And we get 3.3 times 10 to the minus seventh for our Ka. All right, now it says next, calculate the H plus and the pH of the solution, right, after we add our Kx. So we've got to think, okay, what is the pH of the solution if we add in 0.021 moles of Kx? Well, we know the Ka from the first part of our problem, and we now have made a buffer. And so when I have a buffer, remember that I am going to calculate this with my equation like so. All right, so let's see what we know and we can plug in. So we're looking for our H plus, and that's the pH. So the Ka we found to be 3.3 times 10 to the minus 7th. All right, the number of moles of Hb. Well, we know that it was 0.043 molar, and we know it was 1 liter, so that's also 0.043 moles. And then we added to that 0.021 moles of the Kx, right? So we're putting in those pieces of information. And so I get that the H plus concentration now, when I've made my buffer, is 6.76 times 10 to the minus 7th. And the pH is the negative log of that, which happens to be 6.17. All right. Well, the buffer capacity of our buffer is its ability to react with a strong acid or a strong base. And if we think about a buffer, right, eventually you're going to run out of what you have that makes it be a buffer. All right, so let's say that we have a buffer down here, right, and I have some weak acids and I have some conjugate bases. All right, what if I added in, say, some strong base? Well, remember that that strong base is going to react with our weak acid and turn it into a conjugate base. And if I add in another strong base, it's going to react with the weak acid and turn it into the conjugate base. All right, well, if I keep pouring in more hydroxide, well, now it doesn't have any more weak acids for it to react with. It has exhausted those weak acids. And so now I'm just dumping in strong bases. All right, so its capacity is how much strong base, in this case, could I add until I ran out of weak acid? Or vice versa, how much strong acid, right, until, right, we react with all of it until we exhaust it. Well, we can plot this. And when we plot these things, we're going to put the pH on the y-axis, right? Y means the up and down axis. And the number of moles of either our strong acid or strong base that we're adding along our x-axis. So let's see that on our next slide. So here we have a figure of a buffer, all right? And so in between points C and B, we have a buffer. And like I said on the previous slide, we're going to plot the pH along our y-axis there. And so notice that right in point A is what we call the native buffer pH. This is when the buffer is 1-to-1 ratio of acid to base. All right, and so, right, if I have exactly a 1-to-1 ratio of our acid to our base, remember that the pH is equal to the pKa plus the log of base over acid. If those are 1-to-1, then the log of 1/1 or 10/10 or 9/9 or whatever the heck it is, the log of 1 is 0. So that means that the pH is equal to the pKa at the native buffer. All right, so notice that as I add in, say, strong base, the pH is going to slowly start to increase as I do that, right? Because we are converting weak acid into weak base. So the pH is going up as that ratio is changing. Eventually, we're going to reach a point out here at point B All right, well, that is the point in which we have added in so much strong base that we have run out of all of the weak acid. And when we do that, as I continue to pour more and more strong base in, now it doesn't have anything to react with. So now I just have a solution that's weak base and strong base. Notice that the pH then is going to go up really fast after that point. The opposite's true if we go the opposite direction, right? As we add in a strong acid, we're going to react it with the weak base and turn it into a weak acid until we run out of weak base, which is where we're going to have effectively run out of that being a buffer. And as I dump in more and more acid, notice that the pH is going to fall off really quickly after that point. We're going to use this figure again when we look at titrations. So you might want to make note of this figure in case you want to come back and look at it when we talk about that a little bit later on. Next, we can talk about the buffer range, and that is the pH range at which the buffer is effective. And if we look at the previous slide, it was between 5.4 and 7.4, which were points C, right, and B on our figure. That was our buffer range. If you look at the y-axis, right, those are the ranges at which our buffer was, worked as an effective buffer. Once we got above or below that range, it's not a very good buffer, right? And so the buffer range is best, right, when we are closest to a 1-to-1 ratio of our acid to base, right? Our weak acid to weak base in our buffer, whoever's making that up, the better the buffer is going to be, is the better we are, the closer we are to them being a 1-to-1 ratio with each other.